Okay, so as an addition to definitions redox, which is group 1, 2, and 7, we have disproportionation reactions, which is a species in both oxidized and reduced. So both increase and decrease in oxidation number of that species. We have half equations, which are a full redox being split up. So one of them is reduction, one of them is oxidation. Oxidation is loss of electrons, increase in oxidation number, or gain of oxygen molecule. Oxidation number is a theoretical change of an ion. In a covalently bonded ion atom, in a covalently bonded compound, assuming that the bonds become ionic. And then an oxidizing agent is what allows oxidation, so it's electron acceptor, a species that gains electron. Oxidizing agent itself, it's actually reduced, okay? And then we have redox reactions, which is reactions where both oxidation and reduction happen simultaneously. And then we have reducing agent, which is what allows reduction, so it gains electrons, so it decreases in oxidation number. And then we have elements of group 1 and 2. So first, ionization energy. It's actually a small, very important definition. So it's the energy required to remove 1 mole of electrons from 1 mole of a substance in its gaseous atom to form 1 mole of a gaseous plus 1 ion. So you have Mg gas to go to Mg plus gas plus electron. Ionization energy trends is usually down the group. It increases because atomic radius and shielding increases. Nuclear attraction to the outer shell electron is less strong, so it's easier to remove, so you have less less ionization energy required. And then you have solubility for group 2 hydroxide, and increases down the group. And then for group 2 sulfates, it decreases down the group. So test for ammonium ions, it's adding sodium hydroxide in AOH aqueous and gently warming the solution. Ammonia gas will form and turn damp red litmus paper blue if ammonia was present. And then test for carbonate ions is add acidified barium chloride to solution containing sulfate ions. If it formed a white precipitate, then barium sulfate has been formed, so it is a positive test. And then we have thermal decomposition, which is chemical substances broken down by heating. And then we have thermal solubility, which is as you go down a period, more heat is required to break down group 2 carbonates plus nitrates. So increase in size, so more thermal stability, so because like more bonds. And then detailed notes is oil rig, so oxidation is loss of electrons and reduction is gain of electrons. Oxidation number for elements is always 0. Neutral compound adds up to 0, and charged compound adds up to the total charge of that compound. Hydrogen is usually +1, oxygen is -2, halogens are -1, group 1 metals are +1, group 2 metals are +2, usually same as group number. Exceptions are oxidation numbers of oxygen and peroxides, which is -1, and metal hydrides for hydrogen, which is -1 as well. So periodic table, electrons are held in orbitals. So atoms are arranged by proton number plus orbitals. So these orbitals correspond with blocks. We have SDPF blocks. Each element in a block has an outer electron in that orbital. So remember this by the mnemonic second paper, because it says SDP. Elements in the same block act similarly because outermost electron is on the same orbital, so pattern and oxidation number is similar. So S block is usually metals, they lose electrons, so oxidize to form positive oxidation numbers. And then you have P block, which are non-metals, as you can see, and it gains electrons, so reduced to form negative oxidation states. Half equation tips, so used to separate oxidation and reduction reactions. So it must be balanced in terms of species present and charges. Balance, sorry, let me just head out for a minute. So it must be balanced in terms of species present and charges. So balance all species, including H's and O's. Balance oxygens by putting H to O's in. Balance hydrogens by putting H plus ions. And balance charges using electrons that are negatively charged. When half equations are combined, you must cancel out on each side of the reactions the electrons. So properties of group 1 and 2. Atomic radius increases as you go down the group because you have additional electron shells. Reactivity as you go down the group, shielding in atomic radius increases, making the outer electron shell easier to get lost. So reactivity increases as you go down the group. Ionization energy decreases as you go down the group because it's easier to lose electrons, so less energy is required. Reactions with oxygen, so group 1 metals plus oxygen would give you metal oxides. Group 1 plus excess oxygen would give you metal peroxides, and most reactive metals plus oxygen would give you metal superoxide. So most reactive metals, we mean potassium and elements below potassium in group 1. Metal plus oxygen, metal oxide is usually M is the metal group, so it's like 4M plus O2 giving you 2M2O. And then metal plus excess oxygen to give you metal peroxide is 2M plus O2 giving you M2O2. It could always be multiples of this. And then most reactive metals plus oxygen is going to give you metal superoxide, which is M plus O2 giving you MO2. So group 2 metal oxides are very vigorous reactions. So only strontium and barium can form peroxides in presence of heat. So 2M plus O2 gives you 2MO, and strontium and barium actually make M plus O2 to give you metal oxide 2. Reactions with water, group 1 is a vigorous reaction, metal hydroxides and hydrogen gas. As you go down the group, it's more violent, right? So basically, that's what it forms. So 2 lithiums plus 2 waters give you lithium hydroxide plus hydrogen gas. Group 2 metals plus water give you metal hydroxide plus gas of hydrogen. So metal hydroxide is alkali solution. Mg plus 2H2 is going to give you MgOH2 plus H2. So MgH2 liquid is very slowly, but then if you react it with steam, it's very faster because it has extra energy. Bright white flame would be formed, magnesium oxide plus hydrogen, and magnesium oxide is a white powder. So now we're going to reactions with chlorine. So group 1 chlorine plus chlorine gas would give you metal chlorides, which are all white precipitates. As you move down the group, more vigorous, more reactive. So 2Na plus Cl2 gives you 2NaCl, which is also salt, and it should always be solid. And the Cl is a gas. Group 2 metal chlorides plus white precipitate, but different stoichiometry, meaning Mg plus Cl2 is going to give you MgCl2. Again, solid. Group 1 plus group 2 plus water is going to give you metal hydroxide. But this is when you have group 1 oxides and group 2 oxides. And again, metal hydroxide is an alkaline solution. So Na2O plus H2O is going to give you 2NaOH, which is alkali. And then group 1 and 2 oxides or hydroxides plus dilute acid is always going to give you the salt, depending on the acid and the water. So it's a neutralization reaction, meaning an acid and a base form water, and then salt depends on acid. Okay, so we have HCl, sulfate, and nitrate salts. So the chloride salt is made from HCl, sulfate salt is made from sulfuric acid, H2SO4, and nitrate salt is made from nitric acid, HNO3. So group 1 oxides plus HCl would give you 2NaCl plus H2O, and then the same reaction will happen with group 2 oxides. So group 1 hydroxides plus HCl is going to give you lithium chloride plus water, and then same thing for group 2 hydroxide, except it's going to be calcium Cl2 plus 2H2O. So again, solubility of group 2 hydroxides, solubility increases as you go down the group. So MgOH2 is the least soluble, and then barium is the most soluble. So MgO2 is a medicine because it's an antacid, so it acts opposite to an acid, which is an alkali, so neutralizes acid. In agriculture, we use magnesium oxide to neutralize acidic soils. Solubility of group 2 sulfates decreases solubility down the group. MgSO4 is the most soluble, and barium sulfate is the least soluble. So solubility of barium sulfate is actually used in medicine for like barium meals, and barium meals are medical tracers that allow internal tissue to be imaged. Toxic if it enters your bloodstream, but since it's insoluble, you cannot be absorbed by blood, so it's safe to use. And then barium chloride test for sulfate ions makes barium sulfate, which is a white precipitate. Okay, now thermal decomposition. So group 2 carbonates and nitrates makes metal oxide, which is a solid, plus vigorous variety of gases. So again, this is a vigorous reaction. Simply by heating in aerobic conditions, which means plenty of oxygen. Group 2 carbonates plus make CO2, metal oxide, again white powder. And then as you go down to group 2, more heat is needed because carbonates increase in thermal stability. So group 2 nitrates make nitrogen dioxide, oxygen, and metal oxide, which again is a white powder. As you go down group 2, more heat is needed because nitrate increase in thermal stability too. So carbonates and nitrates for group 2 are kind of similar. Thermal decomposition of group 1 metals. Group 1 metal carbonates and nitrates also undergo thermal decomposition upon heating in anaerobic conditions. Lithium acts like group 2 element, so lithium nitrate would give you lithium oxide plus nitrogen dioxide plus oxygen, and lithium carbonate is going to give you lithium oxide plus carbon dioxide. But then other group 1 metals do not react the same way. They rarely go completion. So remaining group 1 nitrates form metal nitride plus oxygen, and remaining group 1 carbonates don't decompose at all because they require really high pressures, which we cannot reach in labs. So thermal stability trend, as you go down the group, it forms more stable carbonates plus nitrates, so you need more energy or more heat. As you go down the group, ionic radius increases for small overall change, so smaller ions have bigger charge density. Smaller ions are able to polarize carbonates and nitrates more, so the more ion is polarized, the less heat is required to separate the ion. So smaller ions produce less stable carbonates and less stable nitrates. So you have tests for hydroxides, which is indicates whether it's an alkaline or not. So identified using damp red litmus paper that turns blue if it's positive, and a universal indicator that turns blue-purple from colorless. So carbonates like CO3 and hydrogen carbonates, which is HCO3-, or acids such as HCl is added to the substance if fizzes, making CO2, and then gas bubbles to lime water, and then if the lime water turns cloudy, it shows that it has CO2. Ammonium test or NH4+, so add NaOH, gently heat, ammonia gas is going to come out. So then hold damp litmus paper, that's red and it turns blue. Then you have flame tests that give like unique color for each one, and how this is done is basically you clean a nichrome wire by putting HCl concentrated into a blue Bunsen burner flame, and you repeat this until no color is produced in the flame. And then you dip the wire into an unknown metal compound, and then place it place the nichrome wire in the flame to observe the color. And then you have group 1, which is lithium, is always red, sodium is orangey yellow, potassium is lilac, magnesium gives no color off, calcium is brick red, strontium is crimson red, and barium is pale red. So formation of colors is due to electron transitions. Electrons exist in orbitals when electrons such as supplied by Bunsen burner energy, flame is absorbed by species. Some electrons will be promoted to orbitals which have higher energy. The electrons will then drop back to the original orbital during this process, and then they emit some energy. Some energy is in the format of light, so color depends on wavelength of the light energy. When some electrons drop back down to the original orbital, the energy emitted may not have been the wavelength. Invisible light part of the electromagnetic spectrum, explaining why not all atoms or ions produce a color in the flame test. So we have other chemical tests such as test for CO2, which is bubble through lime water if it turns cloudy, and then it's because it makes a white precipitate, and if that white precipitate calcium carbonate mixes with water, it makes it cloudy. And then we have test for O2, which is a glowing splint test where you put in an unknown gas, and if it relights, it's oxygen. And then you have a nitrogen dioxide test, which is an acidic gas. So holding blue litmus paper in the test tube filled with gas would cause it to turn red. It could also be recognized by the reddish brown color that nitrogen dioxide has. So then we have acid-base titrations, which is a practical model to identify a solution of unknown concentration, where standard solution of known concentration is reacted with solution of unknown concentration. So basically we have a few compounds and we want to see the concentration of one of the compounds. So we have simple method of volumetric solution, which is weighing the sample bottle containing a solid in a balance to 2 decimal place. Transfer the solid into a beaker and reweight the sample bottle. Record how much solid was added to the beaker. Add distilled water and stir with a glass rod until all solid is dissolved. Transfer mixture to volumetric flask with washings and add distilled water to make a mixture of 250 cm3. Mark on the volumetric flask and then insert a stopper and invert the flask to mix. So common errors made with this experiment is systematic errors on the balance, so you forget to zero error it, and then lost substance in transfer process or overfilling the volumetric flask, which could be reduced by using washing methods and reducing volumes of bottom, reading the volumes from the bottom of the meniscus, which is what I drew there. And then we have titrations equipment, so you have a clamp, you have a clamp stand, you have a B-ray, which is the thing the acid goes in, you have a conical flask, white tile to observe the color more clearly, you have volumetric pipette, you have pipette filler, volumetric flask, funnel, dropping bottle and pipette for the indicator, and the wash bottle that contains distilled water. Okay, so titration simple method is that you fill the B-ray with a standard solution of known concentration. Make sure the jet space in the B-ray is filled with and doesn't contain air bubbles. So the jet space is actually this part. So you make sure that that's filled and doesn't have any air bubbles, and then you use a pipette plus a pipette filler to transfer 25 centimeters cubed of the solution of unknown concentration to a conical flask. Then you add 2 to 3 drops of indicator, record the initial B-rate reading, and then titrate contents to conical flask by adding the solution from the B-ray until indicator undergoes a definite permanent color change. Record the final B-ray reading and calculate the titer volume. Repeat at least until you get 2 concordant results, which means basically results that are close together within 0.1 cm3 of one each another. All equipment comes with their own uncertainty values. These values must be combined to find overall uncertainties of a final answer. So you add them. Usually in percentage uncertainties. So best way to reduce uncertainties is increase the volume and concentration of the substance in the conical flask or decrease the concentration of the substance in the B-ray. So risk assessment is analyzing the equipment, lab environment, chemicals being used, suggesting methods to reduce risks, and what actions should be taken if the risks occur. So indicators and titrations, you could use methyl orange or phenolphthalein. Methyl orange goes red in acid, yellow in base, and could have a pH range of 3 to 4. Phenolphthalein pH range is larger, so 8 to 10, goes colorless in acid and pink in a base. So solution concentrations is measured in 2 different ways: moles per decimeters cubed and grams per decimeters cubed. Inorganic chemistry is trends of halogens. We only talk about Cl, Br, and I. Group 7 is a highly reactive nonmetals. They want a full outer shell, so they gain an electron to form a -1 atom. Ion. Atomic radius increases down the group due to additional shields. Electronegativity. Because atomic radius increases, shielding increases, outer electrons are less strongly attracted to the nucleus, so more easily removed, so electronegativity decreases down the group. Melting and boiling point. So basically they're simple covalent molecules. They're held together by van der Waals forces, and the strength of their forces increases down the group because increase in MR, meaning more energy is required to break them because they have more bonds, so higher boiling point and melting points down the group. So F is a gas, so fluorine is a gas in room temperature, and iodine is a solid in room temperature. Then we have reactivity, which group 7 gains an electron for a full outer shell. So as atomic radius increases, it's harder to attract the negative electron because more shielding, more distance, less attraction from the nucleus, so reactivity decreases down the group. Now let's look at some physical properties of some halogens. So if you have chlorine, it's in room temperature, it's a green gas. In aqueous, it's pale green, almost colorless. And in a non-organic solution, it's almost colorless, pale green. Bromine is red brick red or brown liquid. So basically in aqueous, it's orange yellow, and in non-organic, it's red. Iodine is gray or black solid. Aqueous is brown, and then non-organic is violet, as well as in gas. So oxidizing powers of halogens. So they're really good oxidizing agents because they're good electron acceptors. So oxidizing power decreases down the group because of lower ability to attract E- because of, again, shielding and atomic radius. So any stronger halogen would displace any halide beneath it in the periodic table, and this is because of the reactivity. So more reactive replaces less reactive. Cl2 displaces Br- and I-. Br2 only displaces I-, and then iodine would not displace any halide ions. So we have negative ions of halogen, and then they're really good reducing agents because they oxidize and they donate electrons to reducing species. Reducing power increases down the group as it's easier to lose electrons due to the shielding and atomic radius. So redox reactions between group 1,2 halides and H2SO4 depend on the reducing ability of the halide used. So for fluoride and chloride ions, as you can see, the NaF plus H2SO4 is going to give you NaHSO4 plus HF, or if you use Cl, it's going to be HCl. So no further reaction because they're not strong enough reducing agents to reduce H2SO4. And both hydrogen fluoride and hydrogen chloride, or like hydrochloric acid, are MICE fumes, okay? Bromide ions, NaBr plus H2SO4 makes NaHSO4 plus HBr. And then two of those HBRs plus, again, the sulfuric acid is going to give you Br2 plus SO4 plus water. Again, it's a misty fume from reaction 1, orange fumes of Br2, and choking fumes of SO2 will be observed in the second reaction. HBr, again, in the reaction 2 is going to reduce the H2SO4. And then in iodide reactions, you have NaI that makes HI, which is a misty fume, and then that reacts with H2SO4 again to make SO2, which is a choking gas, and then solid iodine, and then again makes H2S, 3I2, and 3 water molecules, which is a toxic gas and smells of bad eggs. So that is the H2S. Currently, reducing power increases down the group because iodine has more power than fluorine and chlorine. Disproportionation reactions are basically when one of them gets reduced, one of them gets oxidized, so one increasing in oxidation number and one decreasing in oxidation number. So in this example that actually happened. So this actually gets really used in water treatment systems because Cl is used in small quantities to kill bacteria, but it brings some risks because chlorine may be toxic for the human body. However, the benefits of having clean water would outweigh this risk, so we'll still do this. And then chlorine is also used in bleach production. So sodium chlorate is a key ingredient of making bleach, and it's produced via the reaction using disproportionation of chlorine. So 2NaOH plus chlorine is going to give you NaClO plus NaCl plus H2O, which is the sodium chlorate. So if chlorine is reacted with hot concentrated alkali, this proportionates even further to oxidation numbers of -1 plus +5. So if you have a hot concentrated alkali instead of a normal one, so you get +5 and -1 oxidation number. And then if you mix silver nitrate with halide ions, they give different colors of precipitates, which should be like compared to each other to identify what precipitate is what. So it might not always be clear of the color, so then we test it further using ammonia. So if you add silver nitrate to Cl, you get white, to Br you get cream, and to iodine you get a yellow precipitate. And then if you add dilute NH3, Cl dissolves, bromine doesn't change, and iodine doesn't change. If you add concentrated ammonia, your Cl still dissolves, your Br dissolves, but your iodine does not change. And then we have reactions of hydrogen halides. So hydrogen halides in ammonium gas would give you ammonium salts, which is NH4Cl, NH4Br, and NH4I. And then hydrogen is strong acid in solution. So hydrogen halides plus water make dilute acids. This is how we dilute acids basically. So they're strong acids, to reduce their halide ions, we add hydrogen ions from water. The resultant solution down here is an acidic solution because we are adding extra H's. So you can predict properties of other halogens using trends across the group. So we know as you go down the group, they get more reactive, so you could predict it for acetine and for the other ones as well. So then kinetic equilibria, you have activation energy, which is the minimum amount of energy for particles to collide with successful reaction to take place. You have a catalyst, increases the rate of reaction without being changed, and it works by providing an alternative route or a reaction pathway with lower activation energy. Collision theory is when collisions take place between particles that are sufficient energy or higher or equals than activation energy. And then effective concentration or rate of reaction. So as concentration increases, reacting particles get closer to each other, meaning they would collide more, meaning a higher rate of successful collisions and faster rate of reaction. Same thing for pressure and temperature. Increasing temperature means more kinetic energy, so they would move faster, so they would collide more. More kinetic energy means large proportion of particles that will have at least the activation energy and above, so rate of reaction will increase. Then we have a curve distribution, which is Maxwell-Boltzmann distribution, and it shows the distribution of molecular energies in a gas at constant temperature. So area under the graph indicates the total number of particles present, so this never changes. You have the activation energy here, most probable energy, and mean energy. On your x-axis is your number of particles, y-axis number of particles, x-axis energy. Rate of reaction is a measure of amount of product formed and reactant over time. Equilibria in a closed system is where no heat exchange happens between the system and the surrounding, no matter